Welcome to Lecture 32, in which I'm going to discuss electric current. This is something that's probably a lot more familiar to you than some of the more abstract ideas we've been dealing with in the previous few lectures, because electric current is what flows in wires, and it's sort of what you think of when you think the word electricity. You think of the flow of electrons in wires to your light bulbs and your electric stove and down the big power transmission lines and so on. So we're going to get into more practical material in this lecture. On the other hand, we're making a rather profound philosophical switch, because once we allow charge to move, we're no longer dealing with electrostatic situations. Static means charge isn't moving. Everything we've done so far, we've talked about electrostatics, although we've occasionally made some sparks fly, and they were not electrostatic situations. But when we had conductors charged up or capacitors fully charged, we had electrostatic equilibrium. Now we're going to abandon the assumption of equilibrium. We're going to let charge move. We'll see the situations in which it moves. But here's the big thing. The electric field is no longer zero, or doesn't have to be zero, in a conductor that isn't in electrostatic equilibrium. I made a big point. E is zero in electrostatic equilibrium. We're abandoning electrostatic equilibrium. So if you see me talking about electric fields in conductors, I'm not contradicting myself. I'm now relaxing the assumption that we were in static equilibrium. We're letting charge move, and then there can be electric fields. So what is this motion of charge that we call electric current? Let's begin with a definition of it. Electric current is basically a flow of charge. If you want to get really technical about it, it's the net rate of charge crossing a given area. You give me an area, like, for example, the cross-sectional area of a piece of wire. And you can ask, what's the current in that wire? What's the current flowing through that wire? What's the number of coulombs every second crossing the area of that wire? That's what we mean by current. We mean the net rate of charge crossing an area. So the picture here is showing positive charges, a line of positive charges moving along through a conductor, and we want to know what the net rate of charge crossing that area is. In this case, the current, whose symbol is going to be I. Get used to that. I will be the symbol for electric current. That current is moving to the right, and the unit of current, because it's charge per time, is coulombs per second. That's the SI unit. And the SI unit defines the ampere, named after the French scientist Ampere. And he has an accent on the E, but when we write the unit out, it doesn't. And as usual, the unit is not capitalized, but the symbol for the unit, capital A, is capitalized because it's named after an individual. So 1 ampere, also called an amp, given the symbol A, is 1 coulomb per second flowing through whatever area you specify. And usually, but not always, we're talking about conductors whose area is easy to define, like a wire. But in my field of solar physics, we're often talking about conductors, or about charges flowing, currents flowing in the atmosphere of the sun. And then you sort of have to say, well, what area of the atmosphere are we talking about? So it isn't necessarily something that flows in a wire, but it can be, and it usually is. So let's look at some typical examples of currents. I've just defined the unit of current as the ampere, 1 coulomb per second. What are some typical currents we deal with? Well, if you have an incandescent light bulb, the kinds of things that are now being phased out because they're energy inefficient, a typical light bulb of 75 or 100 watts draws a current of about an ampere. Your watch draws a current out of that little tiny button battery of about maybe a microampere. Cell membranes, the membrane that separates the inside and outside of biological cells, is perforated by proteins that make up little channels, and flowing in those channels are electric currents, typically on the order of a picoampere, 10 to the minus 12 amperes, a millionth of an ampere, a trillionth of an ampere, very tiny currents. And those currents are carrying materials like sodium and potassium and other essential products in and out of the cell membrane. If you've got a cordless drill, a nice powerful cordless drill, it's probably drawing about 25 amps from its lithium ion or its other kind of cadmium battery, whatever kind of battery it has, it's drawing about 25 amps. So that's what a cordless drill would draw. Your whole house maybe has a power supply available to it of about 100 amps, maybe 200 amps for a newer house. That's the most kind of current the entire house would be drawing from the power system. The power line itself, big high voltage power lines carrying currents across the landscape, they may be carrying 1,000 amperes of current. So those are typical values of current. An amp is fairly typical for the kinds of things that are going on in your house. Very, very small currents, cell phone in standby mode, 2 milliamps maybe, down to a microamp in your watch, a picoamp in your cell membranes. But an ampere is a typical current somewhere in the middle of this range. So currents range all over the place. Well, Let's look in a little more detail at electric currents. Electric current is a flow of electric charge. We've quantified it as the net charge crossing an area, the rate at which net charge is crossing an area. And I want to emphasize that in the context of the fact that there are two kinds of charges. In fact, in wires, metal wires, the charge carriers that are carrying current are in fact negative electrons. So in this picture, the electrons are moving to the left, but because they're negative, the net flow of charge is to the right, and that constitutes a current to the right. So a current to the right could be caused either by electrons flowing to the left or positive charges moving to the right in this picture. In fact, if we had a situation in which we had both kinds of charge carriers, positive and negative, and the positive ones were moving to the right and the negative ones were moving to the left, we would have a current, and each one was carrying a current of I. We would have a total current, a net current in this system of 2I to the right. And there are systems that carry current this way, some of them in semiconductors, some of them in ionic solutions where you have positive and negative ions both. What happens if I had both charge carriers moving in the same way? Well, I could get that by just picking up a piece of wire and walking along with it. There's no current then, because the flow of positive charge to the right and the flow of negative charge to the right, if they're equal, cancel each other out, and there is no net current flowing in that wire. So the fact that there are charges in a material and the material is moving is not enough to mean that there's a current. There has to be a net flow of charge in one direction or the other. Either positive or negative charges have to be moving while the others are stationary, or, in fact, both could be moving in opposite directions. But if they're both moving equally in the same direction, there's no net current there. So let's talk a little bit more about how current is carried in different kinds of materials, because it isn't just wires, although I am going to concentrate more on wires. So we want to look at mechanisms of conduction in different materials. And again, we'll focus on wires, but we want to look at other materials as well. Back in lecture 29, when I first began talking about conductors, and there I was talking about them in the context of electrostatic equilibrium, here I'm talking about them in the context of their carrying current, we saw some different kinds of conductors. And I'm going to use in this example exactly the same kinds of conductors we're talking about. So same pictures you saw before. Here are metals, as exemplified by this power line. In metals, the current is carried by free electrons. And I'll show you in a moment what I mean by free electrons. Ionic solutions, as, for example, a sports drink, which is high in potassium ions, particularly because they need to move through those membrane channels in the cell membrane to get potassium into the cells and so on. There, the current is carried by both positive and negative ions. That doesn't mean there's current flowing in a bottle of sports drink, but if you hooked two electrodes to a battery and stuck them in that sports drink or in seawater, you would get a current flowing carried by both positive and negative ions. Plasmas, ionized gases, the kinds of things I studied. I mentioned a minute ago that the solar corona, the sun's atmosphere, is carrying currents because it consists of isolated electrons and ions, because it's at 2 million kelvins of temperature, and it is, therefore, the ions and electrons are completely separated. Particularly, hydrogen is separated into protons and electrons. Both are free to move, both carry current. So plasmas, like ionic solutions, carry current both ways. In semiconductors, the devices that make up modern electronics, that make modern electronics work, semiconductors are engineered to have particular concentrations of electrons and something else called holes, which are actually simply the absence of an electron, but they move through the material as if they were a positive charge. And so there are two kinds of charge carriers in semiconductors, electrons, negative, and holes, positive. There's a picture of a semiconductor chip that might be at the heart of a computer, and it's being able to manipulate the concentrations of those two kinds of carriers that makes for all the wonderful things we're able to do with modern electronics. And finally, as I mentioned, there are superconductors, devices that conduct electricity with no loss of energy, perfect conductors. They really exist. This one is repelling itself from a magnet. Its whole thing is immersed in liquid nitrogen because superconductors require very cold temperatures. We would revolutionize the electromagnetic technology industry if we ever developed a room temperature superconductor. For now, the highest temperatures we can get to are a little over 100 kelvins, which is still about minus 200 Celsius, and only a little bit above the temperature at which, say, air liquefies. But in superconductors, a complicated mechanism involving quantum mechanics causes electrons, even though they're widely separated, to get paired, and then they kind of move as waves with no resistance, no loss of energy through the conductor. So there are some important conduction mechanisms. But by far the most common one, the one we think about most, and the simplest one in some ways, although it's not that simple, is the conduction in metals, current carried by free electrons. I want to emphasize, though, before I look at metals, that if the only things that carried current were metals, a lot of the interesting things we can do with electricity would not be possible. We wouldn't have semiconductors. If everything behaved the way a metal did, electricity would be a much duller subject. So let's take a look at conduction mechanisms in metals in particular. And I'm going to move to the big screen, not because we're going to do calculations, but because I need to be able to point out what's happening here. So let's go and take a look at conduction mechanisms in metals. Conduction in metals. First of all, a metal, you don't perhaps think of it this way, but a metal is like any other solid, or like most solids, exceptions are glass and a few others. Solids, if we let them form naturally and sort of cool down slowly, they tend to form regular arrays of atoms, which we call crystals. So the crystal structure is called a lattice. It's a regular spacing. And here's what happens in metals, and this is what makes a metal a metal. In metals, the outermost one or two electrons of the individual atoms are so loosely bound to their atoms that when the whole structure forms together to make a crystal, the electrons become freed from their individual atoms, and they're able to wander through the metal. They can't leave it, because if they did, the remaining positive charge would try to pull them back. But they can wander freely through the metal without being attached to individual atoms. Now, most of the electrons remain attached. There are many electrons in an atom of a metal. Iron, for example, has 26 electrons, and only the outermost one in, say, iron would be free to move around. Iron's not a very good conductor, by the way. So there is a sea of free electrons that is surrounding the positive ions. And these free electrons are free to move. And in fact, they do move. And at ordinary temperatures, they are moving around randomly at pretty high speeds. So here's what the situation looks like. We're going to focus on one electron and see how it behaves. Now, before I go on, I have to tell you, I'm giving you a sort of classical physics picture of a phenomenon that really can only be explained thoroughly using quantum physics. But it gives us a good idea of what's happening. So if I focus on one electron, it's in random thermal motion. It's kind of bouncing around in there, and frequently it hits these ions. And when it does, it typically gives up some of its energy, but it also may gain energy back from the ions. And in a state of equilibrium, it's basically just bouncing around at roughly a constant and rather high velocity, typically hundreds of meters a second. And there it goes, and it's bouncing around randomly. And it doesn't, on average, go anywhere. I mean, maybe one electron wanders somewhere through the metal, other one wanders back the other way. There's no current. There's no net flow of electrons in this thing. Now let's ask what happens if we put an electric field in this metallic conductor. Remember, I said electric fields are okay now in conductors because we're dealing with situations in which we have not got electrostatic equilibrium anymore. We've got a dynamic situation in which charges are moving. So let me put an electric field here that points to the right. These are the field lines. Electrons are negative. Charges experience a force QE in an electric field. So the charges here experience a force to the left. The electrons experience a force to the left. Now that force is actually relatively weak, and it isn't going to have a huge effect on the electron's motion, but it does have a little bit of an effect. So as the electron bounces randomly around in the material, here it goes, there is a slight bias. Each time it bounces, it's being dragged a little bit further to the left. And so as a result, despite its random motion, it ends up drifting slowly, bouncing around to the left. And I really mean slowly. Remember, that electron is bouncing around at perhaps hundreds of meters a second due to that random thermal motion. The speed of that drift, and we call it a drift velocity, it's sort of an average velocity, that is very, very slow. It's typically millimeters per second. The electrons carrying the energy, carrying the current in wires flowing in your home are typically moving at millimeters per second. Now, don't confuse that with the speed at which the electrical energy and the electrical impulse travels. That's close to the speed of light. But the electrons themselves, I think we often focus too much on the electrons. It's really the energy in the fields that's important. And the electrons are moving very slowly, typically millimeters a second. It's a little bit like a car going through city traffic. You accelerate, you get up to 20 miles an hour maybe, then you slam on the brakes, and you may be moving pretty fast in between red lights or other obstructions, but your average speed is much lower, and that's kind of what's happening here with the electrons. So the electrons drift very slowly with some velocity, some average slow velocity. But here's the important thing. If I were to increase the strength of the electric field, you can imagine that that slight influence it has is going to increase, and the drift velocity is going to increase accordingly. And so the electrons are going to go faster, and if there's a bunch of electrons drifting that way, there will be a current, and the current will depend on the strength of that electric field. So let's look at that in a little bit more detail. In the presence of the electric field, as I indicated, the electrons acquire this slow drift velocity, and because they're electrons and they're negative, it's opposite the direction of the field. And the drift velocity will be proportional to the electric field. Bigger the electric field, the bigger the little bit of change that develops in the rapid random thermal motion of those electrons. The electrons are negative, so there's a current in the direction opposite the field. So current is proportional to this drift velocity, but with a negative sign. It's proportional to the opposite of the electric field. But they're proportional. The voltage across the conductor is also proportional to the electric field, because when I have a conductor with an electric field in it, nice uniform electric field, voltage is electric field times distance. And so what that means is that the current is proportional to the voltage in a conductor like a metal. So here's a picture of the situation. I've got a voltage V across the conductor, some length of conductor. I've got electrons drifting leftward opposite the electric field, and they constitute a current I flowing to the right. And my claim is that current is proportional to the voltage. Now, that is not an exact, profound, deep result. That's approximately true for metals. If the electric field gets too big, that's no longer true. If the metal gets down to too low a temperature, that's no longer true. But it's approximately the case that the current is proportional to the voltage in an electrical conductor like a metal. And that leads us to something you've probably heard of called Ohm's law. Ohm's law is a relationship between electric voltage and current and another quantity that characterizes the conductor, namely its resistance, how it slows down the flow of current. So in many conductors, current is proportional to voltage. The proportionality is this property of the conductor called its resistance. It's how much it impedes the flow of current. The resistance R depends on the material properties, like the density of electrons in it, like the crystal structure, like the presence of impurities. It depends on temperature. Usually as the temperature goes up for metals, the resistance also goes up. It depends on the size and shape of the conductor. And all of that, though, put together, give you this simple relationship between current and voltage. And you can think of the voltage as kind of a push it's energy per charge. It's kind of a push trying to push current through a resistance R. The bigger the voltage, the more current you'll get. The bigger the resistance, the less current you'll get. That's Ohm's law. Now, I want to emphasize some things about Ohm's law because it's widely misunderstood. First of all, Ohm's law is not some deep, profound law of nature like Coulomb's law for the electric force or its equivalent Gauss's law. Those are deep, profound laws that describe all of nature. Ohm's law is an approximate law that describes how some materials, particularly metals, behave. It's empirical. It's something we observe in the world, and we can kind of figure out why it ought to be true, but it's only approximately true. Good approximation. It's especially true for metallic conductors. Now, if you're going to use Ohm's law, and we'll be using Ohm's law in the next few lectures, be careful. Know what the terms in it mean. V is the voltage across some resistance R. It's not just some random voltage anywhere in a circuit. If you've got a 6-volt battery in a circuit, that doesn't mean V for Ohm's law is 6 volts. It might be, depending on how that battery is connected, but it might not be. V is the voltage across a particular resistance R. I is the current through that resistance. Note those two words. Voltage appears across because potential difference is a property of 2 points. Current goes through because it's a flow. And if you use those words and think about them when you talk about voltage and current, you won't go wrong. And R, finally, is the resistance we're talking about. There are alternate forms of Ohm's law. They aren't different laws. It's just algebra. V is IR. R is V over I. You can put them all together. And that tells you, by the way, that the unit of resistance is the volt per amp. And that unit is given the name ohm. And the symbol for an ohm is a capital Greek omega. So there's a Greek letter we're going to have to deal with. So now we understand Ohm's law. And let's see if we really understand it by doing a quick calculation based on our understanding of Ohm's law. So let's go to our big screen again. And let's look at a real practical situation. Okay, here's a car battery, and car batteries have these lead terminals that come out of them, and car batteries got acid in them and all kinds of stuff, and a lot of corrosion can occur at a battery terminal. You may have looked at your battery in your car sometime, seen all this white corrosion-y stuff on white stuff that forms on it. And corrosion can increase the resistance of the contacts that connect that to the very thick wires that carry current from that car battery. And in this case, corrosion has increased the resistance of the battery to about 0.03 ohms, I'm telling you. And I'm telling you that the starter motor, by far the biggest current drain in a car, draws 130 amps. That's a big current. That's why the wires from that battery have to be so big. So let's ask, what's the voltage across the starter? It's a 12-volt car battery. You might think the starter is designed to run on 12 volts, and it probably is, but it can run on less voltage too. A typical fairly good battery with a fairly good starter, the voltage across the starter will end up being somewhere between 9 and 12 volts, and I'll show you in subsequent lectures how we figure that out. But here, just based on this resistance, we're going to ask the question. So we can easily do that because the voltage across that resistance is related by Ohm's law to the current through that resistance and to the resistance. And we're given the current, it's 130 amps, that's flowing from the battery through that battery terminal with its resistance and through the motor, starter motor, and back. And that is 130 amps times 0.03 ohms. That's 3.9 volts. So that leaves the car battery voltage, well, the car battery voltage is 12 volts. That leaves 8.1 volts across the starter. That's a little bit low. You probably hear, oh, when you try to start that car. It's not that low. You're probably going to start. But it's not as high as we'd like it to be. Well, let me move on and end with two other topics involving electric voltage and current. First of all, power, and then we'll look at electric safety. So let's consider electric power. We know that current is charge per time. We know that voltage is energy per charge. Multiply them together, you have charge per time, energy per charge. The charge cancels, and what have you got? You've got energy per time. We know way back from mechanics that energy per time is a measure of power. That's what power is. It's the rate at which we're using, consuming, generating, whatever, energy. So the power in SI units is measured in watts, and it comes out with voltage and current. You could work out the units in detail. It comes out in watts. So if you multiply voltage and current, you end up with power in watts. Electric power is P equals IV. And if you know Ohm's law and you're dealing with a resistance, you can write that in two alternate forms, which look like they're contradictory, but believe me, they aren't. You have to think carefully about them. If we take V is IR, we'll get power to be I squared R. If we take I to be V over R, we'll get power to be V squared over R. Two alternate forms. And I'd like to give you an example of that, of understanding electric power, and that's the example of electric power transmission. You see transmission lines going across the country, and they carry very high currents. Well, not that high, 1,000 amps maybe, but more importantly, they carry very high voltages. 345 kilovolts, for example, 750 kilovolts. There are power lines in some parts of the world that are carrying over 1 million volts. Why do we use high voltage for power transmission? Well, we can understand that by understanding electric power and resistance. So let's look at an example. Here's a picture of a power plant on the left, a transmission line carrying power to a city on the right, and I'm going to assume a current I is flowing in that transmission line and that there's a voltage V between the transmission line and the ground, and sometimes we use the ground as sort of the return wire. I'm going to assume that happens here. It's not usually done these days, but it will make my calculation a little bit more straightforward. So the power plant is supplying some power P. That power is the product of this voltage and current. So the power transmitted to the city is P equals IV. We could possibly transmit that with a very, very large current and a relatively small voltage. Or we could do it with a small current and a large voltage. Well, the power lost in the transmission line, whose resistances R, is I squared times R, as we just saw by applying Ohm's law to that expression for power as the product of voltage and current. And so if you increase I, you increase the power loss. And that is the reason we don't like large currents in transmission lines. We would like to keep the current relatively small, and to supply the same power, we've got to make the voltage very, very big. That's why we transmit power at very high voltages. The best choice is a relatively small current and a large voltage. Electric power transmission, and why we do it the way we do. More on that later. Well, let's end up with a quick look at electrical safety. I had a danger high voltage sign up here a few lectures ago. We worry about high voltages, but some people are a little more sophisticated and say, it's not the voltage that gets you, it's the current. Yet we don't see danger high current signs. There's no sign in your car that says 130 amps flowing here. So why the issue? Well, the issue is this. It really is current that is the dangerous thing. Current passing through your body is dangerous. But it takes a certain amount of voltage to drive current. Your body, under normal dry conditions, has a resistance of tens to hundreds of thousands of ohms. And it would take a very high voltage indeed to drive significant current through you. So it's neither high voltage nor high current alone that's dangerous. It's a combination. You have to have voltages that are high enough to drive big enough currents through you. The currents it takes aren't that big. Currents through your heart of microamperes will upset the electrical system. Your heart is an electrical system, as we've seen, that paces your heart. So they can be pretty small. but usually you don't get currents very big inside your body unless you've introduced some kind of electrodes into it. So let's look at what's going on here. Current is what's really dangerous to us, but it takes voltage to drive that current. Here's a little table that shows you some of the currents that and their physiological effects. You get about a milliamp, half to 2 milliamps flowing through you. You could barely feel that. Up to about a factor of 10, more than that, 10 to 15 milliamps in your muscles, which are also electrical systems. In fact, your nervous system is electrochemical, so it's upset by these kinds of things, by electric currents. Your muscles will contract involuntarily. You may not be able to let go of something you grabbed at some high voltage. Go a little higher, 15 to 100 milliamps, thousandths of an amp, up to about a tenth of an amp, you get a severe shock and your breathing may become difficult. At 100 to 200 milliamps, that's actually the most dangerous. Your heart will go into fibrillation and you'll die within a few minutes if you're not resuscitated. Above that, you may get cardiac arrest, which is actually easier to restart you out of, but you may get actual burns from the resistive heating and your breathing will stop, but you can be resuscitated. Not by somebody who doesn't first disconnect you, though, from the source of the problem. So let's look a little bit more at electrical safety. We'd like to keep ourselves safe in the electrical context, and one thing we do is to use the fact that the earth ground provides us with a nice zero of potential, and one side of the electric power line is in fact grounded. So here I have a picture of somebody operating an electric drill with 2 wires supplying it from an outlet in the wall. And one side of that power line is, as I say, grounded. The other side is the so-called hot side. The grounded side is called neutral in electricians' parlance. What happens if there's a short circuit between the hot wire and any piece of metal on that case of that drill? If it's an older drill, it's probably made of metal. These days it's made of plastic, but it may still have screws and things sticking out. Well, if there's that short circuit, meaning a place where a wire that's supposed to not contact that metal case does so, then I can get a current to the case, and a current could flow through me and, in the worst case, electrocute me or give me a serious shock. So to avoid that problem, many devices that we're likely to use in situations where we'd be in contact with grounded things like water pipes, for example, so in the kitchen with power tools and so on, we add a third wire, a ground wire, and then if there's a short circuit to that case, the current flows down the ground wire and it breaks the circuit breaker or the fuse that protects that circuit from short circuits, which could otherwise cause fires because too much current would flow. So the reason you see grounding prongs, and let me show you some, the reason you see prongs like this third prong on this piece of conductor, this conducting prong, this big round one, is because all the metal parts of this power supply, the one I used to charge the capacitor in the previous lecture, all those metal parts are connected directly to this prong. And that means if anything goes wrong in here and high voltage gets somehow connected to the metal case, it will simply blow the fuse and I will be safe. So that's one way of protecting us from the danger of electric shock. Here's another way. In a lot of modern plugs, one prong is wider than the other, and that goes into the outlet in only a certain way, and that's designed to make it less likely that the hot wire is going to short circuit to any piece of metal, like this little piece of glue gun here, where there's a metal tip that might pick up high voltage if, in fact, something went wrong. You want to be even safer, you use devices called ground fault circuit interrupters. Here's one that's built into a hairdryer, because a hairdryer would be used typically in a wet environment of a bathroom. Many of them are also built into electrical outlets. You'll see outlets in bathrooms, particularly near swimming pools, in basements, outdoor outlets that have these extra buttons that are for testing the ground fault interrupter. And what the interrupter does is it senses the current flowing down one wire and the current flowing back the other wire. And if they aren't exactly equal, it assumes the current is leaking off somewhere, possibly through a person, and getting to ground some other way, and somebody's getting shocked, and so it shuts off the circuit before a dangerous current can develop. So those are some ways of protecting us from the dangers of electricity, the dangers of too much electric current flowing through us. Well, let's end by taking a look at what we've learned in Lecture 32. We've learned about electric current, the flow of electric charge, movement of electrons or other charges through electrical conductors. The unit is the ampere, equal to a coulomb per second. We've seen several conduction mechanisms, especially and most importantly, we looked at metallic conduction. The electric field and the electric electron-ion collisions give rise to this drift velocity proportional to the field. That leads us to Ohm's law that relates the current, the voltage, and the resistance of that particular piece of conductor. We've seen then that electric power is the product of current and voltage. And finally, we've looked at electrical safety.